Okay, and welcome back. We're in the first episode of the fourth season, chapter 4. And we're looking here at combining functions algebraically. I know that sounds intriguing and fun, so let's get right at it. Let's just remind you quickly of your function notation. If we have f at x equals that, determine f at 0. So when x is 0, just slap that baby right in there, and we've got so 4 times 0, that's 0. That one zeroes out. We get left with 3. So f at 0 is 3. That's also the x-intercept, the y-intercept, because we let x equal 0. For this next section here, I know how everybody loves to not have to listen to my voice, so we're going to listen to Liddy.
Consider the graphs of y equals f at x and y equals g at x. The sum of the functions f at x and g at x is f at x plus g at x. This may also be written as f plus g at x. I'll let h at x.
This is the notation that I will be using more often, is the f plus g at x.
Equal f at x plus g at x. Here is the graph of y equals h at x. The y-coordinate of any point on the graph of y equals h at x can be determined by adding the y-coordinates of the corresponding points on the graphs of y equals f at x and y equals g at x. So, to determine the value of h at 2, add f at 2 and g at 2. F at 2 is 2. G at 2 is -1. So h at 2 equals 2 minus 1, which equals 1.
So the domain is now the thing that we have to look at. If we look at the original f of x, the domain that we had was x is greater than or equal to -2. If we look at g at x, hey, that was a line. It's always XER. But if we look at what we have this new h, notice what happens with the domain there. The domain took on that restriction of the more restrictive original function. And without further ado, because that lady did such a great job of explaining, we're going to have her explain this subtracting.
Consider the graphs of y equals f at x and y equals g at x. The difference of the functions f at x and g at x is f at x minus g at x. This may also be written as f minus g at x. I'll let d at x equal f at x minus g at x. Here is the graph of y equals d at x. The y-coordinate of any point on the graph of y equals d at x can be determined by subtracting the y-coordinates of the corresponding points on the graphs of y equals f at x and y equals g at x. So, to determine the value of d at 2, subtract g at 2 from f at 2. F at 2 is 2. G at 2 is -1. So d at 2 equals 2 plus 1, which equals 3.
Ooh. So now that you did your subtracting, let's see if the domain holds up as well as it did before. Okay, so the original was greater than or equal to -2. Our original g of x was all the real numbers. When we did our d of x, hey, look at that. The domain also took on the more restrictive of the two original domains. All right, adding was good, subtracting was good. Let's check it out, that multiplying. She'll just continue right on for you.
Consider the graphs of y equals f at x and y equals g at x. The product of the functions f at x and g at x is f at x times g at x. This may also be written as f times g at x. I'll let p at x equal f at x times g at x. Here is the graph of y equals p at x. The y-coordinate of any point on the graph of y equals p at x can be determined by multiplying the y-coordinates of the corresponding points on the graphs of y equals f at x and y equals g at x. So, to determine the value of p at 2, multiply f at 2 and g at 2. F at 2 is 2. G at 2 is -1. So p at 2 equals 2 times -1, which equals -2.
I tell you, what more could you ask for in those videos? Let's keep looking at the domain now again. So, our original f was our red one. Okay, we knew that one. We know the other one. What happens with the domain on this one? Oh, again, it's the more restrictive. So the way they're showing it is that when we add, subtract, or multiply functions, the domain of the new one is whatever's in common between the two. We're looking at what's the common domain, what's the most restrictive coming from the two original. Alright, time for us to try it out and see what we can do with it. Okay, we've got these two functions. Let's do the domain and the range. So, domain for f. Let's do our domain is, hey, that's a line, so that's xer. And the range is going to be yer because it's just a line. For g of x, hey, we've got absolute value, so we know that that's a kind of looks like that v thing. Your domain, again, xer. Your range, though, this time, it can't be negative. We can put a negative x in, but the y value is always going to be positive. So it's going to be greater than or equal to 0. Okay, now we're looking at adding the two functions together. Well, let's do that. Let's take our f of x, f at x, which is, I'll give you the other notations too, because they could give you the same question by saying f plus g at x, which is the same thing as saying take the f of x and add to it the g of x. Let's plug in the equations. This is just a game of substitution. Wherever you see f at x, we put what f at x is. Substitute in x plus 2. It's a good idea to throw in brackets whenever you substitute. Plus g at x, hey, that's the absolute value of x. Those are brackets already, so we'll leave it like that. Can't go any further, can't combine anything. So now we look, that's our explicit equation. Let's get the domain and range. Our domain, both of them had a domain of xer, so hey, this one's going to be xer. But for the range, we're going to use technology. We're going to look at what the graph is, and we're going to read the range off of the graph. So into your graphing calculator now. So we want to plug into our y equals whatever our h of x was. Okay. If you can't remember where the absolute value is, hey, it's down. Just go second catalog. It's on the 0. It's the first one there. Can't remember where anything is, they're all in there. And then we graph it. Oh, look at that. 2, 2, 2, 2, 2, 2, 2, and up. If you need to, you can always look at the table as well and see, hey, what's going on here? Look at that. Everything is 2 up until 0, and then after that it goes up. So then that there tells us that our domain was xer, but our range, whenever x was less than or equal to 0, h at x was equal to 2. Wherever we had an x that was greater than 0, we saw that h at x, hey, it went greater than 2. It kept going up 2, 4, all the way up there. So if we look at these two things, we can say, hey, that range is always greater than or equal to 2. Okay, so to recap, domain comes from whatever's in common between the two previous original domains. Range, use technology, look at what the graph is. I know you're missing the explanation from the lady, so I'm going to give you back to her.
Consider the graphs of y equals f at x and y equals g at x. The quotient of the functions f at x and g at x is f at x divided by g at x. This may also be written as f divided by g at x. I'll let q at x equal f at x divided by g at x. Here is the graph of y equals q at x. The y-coordinate of any point on the graph of y equals q at x can be determined by dividing the y-coordinates of the corresponding points on the graphs of y equals f at x and y equals g at x. So, to determine the value of q at 2, divide f at 2 by g at 2. F at 2 is 2. G at 2 is negative 1. So q at 2 equals 2 divided by negative 1, which equals negative 2. Note that when g at x is 0, q at x is undefined. Since g at 1 equals 0, the graph of y equals q at x is a vertical asymptote at x equals 1.
Oh yeah, asymptotes. Hey, this is a rational function. Those things had asymptotes with them. Okay. So when we look at that original function, whatever was in the denominator, which happened to be the g this turn, wherever that crosses the x-axis, those zeros, hey, that's going to be an asymptote. And again, back to the domain question. Okay. The original was greater than or equal to negative 2. So our q is greater than or equal to negative 2. But, so we looked at which one was most restrictive, but we've also got this asymptote that we have to account for as well. So just like you did your vertical asymptotes in the rational section, wherever the denominator goes to 0, you got an asymptote, a vertical asymptote there, the NPVs. Oh, forgetful me, I forgot to do part C. We've got to go back, let's do that one. We were supposed to do the multiplying. So we've got P at X equals, and the way that they can show this in the other notation is F dot G at X. It means the same thing as f of x multiplied by. So then we've got our f, which was x plus 2. Make sure you put brackets. You have to put brackets for this one. Multiplied by absolute value at x. We can't simplify that any further. But let's look at our domain and range. Again, the domain. Take what's in common, the more restrictive, so we know XER for both of them. This one's going to be XER. Range, again, we're going to go to technology. And we're going to graph that. And let's look at what it looks like. And we look and say, hey, ooh, look at that. It's YER as well. All right, number 2. This is fun. Here we go. We got f at x. We know domain and range. Hey, this one, we know that, whoops, x, we do that, x greater than or equal to 0. Can't have the square root of a negative number, and therefore y greater than or equal to 0 as well. And then our g. Hey, that's a line. We've got XER, YER. That is the G, and this one was the F. Now when we get our explicit equation, that means bring them together and actually divide them. Q at x is equal to the F, which was root x, over x minus 2. Our domain of this one is going to be, again, the combination, whatever is most restrictive here. So x greater than or equal to 0. But because we're dividing, we've got to remember we've got NTVs here. X minus 2 cannot equal 0. X can't equal that 2. So we've got to slap that in on there as well. X can't equal 2. We've got a point of discontinuity happening in there. Now, just as an aside, what would happen if this was x plus 2 that we had going on here? That would have put this as x cannot equal negative 2. But if x has to be greater than or equal to 0 anyways, then that would just become extraneous, redundant information. If x had to be greater than 2, or greater than 0, and we had x can't be negative 2, well, of course it can't be. This tells us it can't be. So this one we do include both, because this is inside the original set. Oh my goodness, what's going on here? We've got h of x, and they're saying, hey, let's work backwards. This is Jeopardy. What could be used to make up this? And there's lots of different examples, lots of different ways of doing this. So even the way that I'm going to show you, hey, that's not necessarily the only way. We need to have 1, 2, 3, 4 different functions made up of this. We've got to split it up 4 ways. The easy way would be to split it up as 1, 2, and 3. Each term has their own. That's only 3. I'm going to have to somehow split up one more into there. And I'll split up the first one. I'm going to split up the 4 into 2 different parts. I'm going to say the 4 is made up of 3 and 1. I'm adding, so we can add all these up. We can say that f at x, let's just make that equal to the 3. G at x, let's make that equal to the 1. Those two together made the 4. Then n at x, let's just use the next term, 5x. And m at x equals 2x cubed. That's the most basic of the forms. You could have done anything here. You could have been creative. And I encourage you to be as creative as you can with these. Have a bit of fun with them to make them work. Don't just always take the most basic form. Now we're going to do the same thing, but this time, instead of adding 4 of them, we're going to take it and just subtract 2. So we've got to come up with 2 different ones now. I'm going to once again just go with the easy route. I'm just going to split it into 2 different parts. Hey, let's just take... I'm going to take these first 2, just make that f at x. And because I've got to subtract and I've got to turn the subtracting into an adding, I'm going to say, hey, that must be minus a negative 2x cubed. All right, so then g at x is just going to be negative 2x cubed. And again, you could have taken a whole bunch of different, more creative views of it. And that's what it's asking here now. Hey, you come up with 2 other ones that could have been used instead of the one I chose. Pick something else off for yourself. Okay, so for any of this algebra, there's always good calculator tricks that you can use to check things. Use it to check, not to do the thinking for you. And this part here explains what to do. You can graph, let's say, 3 different functions, 1, 2, and 3, and 4. Hey, you could do 5. You can add them together. The way that you get the y1, y2, y5s, all that kind of fun stuff is right here. You can check that on your calculator for yourself. Okay, getting real fancy here now. X squared minus 9 made up of 2 functions that we multiply together. Hey, that means we're just doing the opposite. If we were multiplying together is a fancy way of saying, hey, expand those. The opposite of expanding is factoring. If we factor this original, we can get 2 factors that would multiply together. That's all they're doing, is asking you a fancy way of factor this. So let's factor it. So p at x is made up of, hey, that's a difference of squares, x plus 3, x minus 3, So then that means that F must be this one, G has to be that one. Doesn't matter what order you put them in. That's all. So F at x equals x plus 3. G at x equals x minus 3. And finally, we're told, hey, we need q of x to equal x plus 1, but be made up of two different things. Well, that means that we've got to be left with q at x has to be equal to x plus 1. But we need to have divided some common factor. Pick any factor you want. It really doesn't matter. You can be creative in here. You could say, let's just use x minus 2. Doesn't really matter. And so we can cancel those off. But if we do this, we're also going to have a restriction that would be added into the x plus 1, where x cannot equal 2. So in that case, it's better to not use something that's going to be having a restriction, but let's try to think of something that wouldn't have a restriction. Well, x squared plus 1 does not have a restriction because we take this denominator, x squared plus 1 cannot equal 0, x squared cannot equal negative 1, x cannot equal the square root of negative 1. Oh, that's an imaginary number, means no NPVs. So I'm going to use this one instead, because then that's going to mean I'll have exactly x plus 1, no NPVs, no restrictions involved in that one. We can expand that numerator, which will give us x cubed plus x squared plus 1 over x squared plus 1. And let's just put this in descending order. X cubed plus x squared plus x plus 1 all over x squared plus 1. And there's our final answer. And again, just hit your discuss the ideas, solidify what you've learned here.